In this lesson, we are going to learn how to calculate the pH of a polyprotic acid. So, what's a polyprotic acid? A polyprotic acid contains two or more ionizable protons. For example, this sulfurous acid, H2SO3, this is a diprotic acid because it has two hydrogens that are ionizable to make it acidic. The phosphoric acid is a triprotic acid because it starts with H3, meaning it implies that we have three ionizable protons or hydrogens in that acid. Usually, a polyprotic acid ionizes in successive steps, and each step has its own Ka. For example, the citric acid ionizes in 3 steps because it's a triprotic acid. The first step has a Ka of 7.4 times 10 to the negative 4th. Now, keep in mind here, we only removed one hydrogen from that citric acid in the first step, and that creates that conjugate base of H2C6H5O7 negative. That product is the reactant in the next step, is the acidic reactant in the next step. And that next step has a Ka of 1.7 times 10 to the negative 5th. Now the HC6H5O7 2 negative, that product, now becomes the acid reactant in the final step. So in that final step, we will be removing that last hydrogen to form H3O plus ions. Now the Ka for this step is 4.0 times 10 to the negative 7th. So see how each step we remove one H ion to make H3O plus, and each step has its own Ka value. One thing you're going to notice about these Ka values is that they decrease as we move down in the steps. So that means that the first dissociation or the first reaction is going to produce the most hydronium, and the last step is going to produce the least amount of hydronium because it's the last hydrogen is going to be very difficult to remove. It's not going to be removed as much because the Ka value is so low, that constant is so low. Let's take a look at what happens if we dissolve something like phosphoric acid in water and what sort of mixture of products we get from that. So we have this phosphoric acid in water. Now, for sure, we're going to get H3O plus. We're going to get hydronium, and we're also going to get a whole bunch of other ingredients as well. We're going to get some H2PO4 minus. This is the conjugate base for the first step, and then we're going to get some HPO4 2 minus. This is the conjugate base for the second step. And then we're going to get some PO4 3 minus. This is the last ion that's produced in the last step. Now, we're going to have way more H3O plus than anything else in this mixture of products. We're going to have the most amount of H3O plus here. We're going to have a little bit less H2PO4 minus because H3O plus is created in every step, so we have the most of that. Now, the most of the conjugate bases is the H2PO4 minus. We're going to have some of that. We're going to have a little bit less of the HPO4 2 minus, and then we're going to have barely any PO4 3 minus because barely any is created in that third step because the Ka would be so low. Now, another thing that you may not have taken into consideration is the fact that there's also probably just a little bit of OH minus in this solution as well because this solution's in water. It is floating around in water, and there is always going to be a little OH minus in that water. So let's take what we know about polyprotic acids and calculate the pH of a 0.100 molar solution of H2CO3. So this is carbonic acid. This is a diprotic acid. And what we're going to do first is just write out the equation, or the reaction, I should say, for the first step. So the first dissociation, removing that first hydrogen, gives us HCO3 minus as our the anion that's produced, the conjugate base. So the Ka, or the equilibrium constant expression for this, is going to be H3O plus and HCO3 minus over H2CO3, the concentration of the carbonic acid or the H2CO3. I'm going to fill in an ice table here. So I'll start with the reaction. I'm going to leave out the water. So I have H2CO3 in equilibrium with the hydronium ion and the HCO3 negative ion. My initial concentration, this is what I'm given. This is the molarity that I'm given. So 0.100. I have about 0 H3O plus and 0 HCO3 minus to begin with. Now I'm going to lose carbonic acid and gain products in this equilibrium reaction. So we have negative X's and plus X's, and then I sum my columns to get my equilibrium concentrations in terms of X. So now I'll substitute in my values. I know the Ka for this is 4.3 times 10 to the negative 7th. And that's the first Ka. That's the Ka for the first removal, the first hydrogen being removed. And then I fill in my equilibrium concentrations. Now, because this Ka is so small, what I can do is I can eliminate the X from that subtraction problem. So that makes life pretty easy for us in terms of doing the math here. So I'm going to eliminate the X. Anytime you're subtracting a very, very, very small X, it's almost like nothing happened. It's almost like you did nothing there. So then I just take 4.3 times 10 to the negative 7th times 0.1. So I'm just cross multiplying here. So X squared is equal to 4.3 times 10 to the negative 8th. I will take the square root of both sides. Now the square root of X squared is just X, and the square root of 4.3 times 10 to the negative 8th is 2.07 times 10 to the negative 4th. So I have 2.07 times 10 to the negative 4th. Now this is my X. But ultimately what I want is my hydronium concentration. So my H3O plus concentration is equal to that X value, so 2.07 times 10 to the negative 4th. Now, this is the hydronium concentration only after the first step. So what I need to do is basically set up an entirely new ice table for the second step. And we're going to see some common ion sort of things happening with the second step. So we have to be very careful about how we fill in this second ice table. So we have HCO3 minus is, it was the product in our first reaction, and now it's the reactant in our second step or second reaction. And that's with water producing hydronium and then the carbonate anion, so CO3 2 minus. So that HCO3 minus was the product in our first step and the reactant in our second step. The equilibrium constant expression for this second dissociation is the concentration of the hydronium times the concentration of the carbonate, the CO3 2 minus, all over the concentration of the HCO3 minus. So let's fill in this ice table. We have HCO3 minus. I'm going to leave out the water in equilibrium with H3O plus and CO3 2 minus. Now my initial concentration of the HCO3 minus, that's not going to be that 0.1 that I'm given. Where I get that is from the previous step. I created a whole bunch of HCO3 minus in that previous step. That's the stuff that will be dissolving or dissociating or ionizing in the second step. So I use that as my initial concentration. I also produced a whole bunch of other things. I produced some H3O plus as well, and I have no carbonate initially from that step. So I complete this ice table by summing the columns, and it's really hard to squeeze my writing in here. I made this too small. So hopefully you can read that. I have 2.07 times 10 to the negative 4th minus X, and then I have 2.7 times 10 to the negative 4th plus X, and then I have X for my carbonate. So I substitute in my values, and I get 5.6 times 10 to the negative 11th. This is the Ka2. This is the Ka for the second step, the second dissociation for carbonic acid, that second hydrogen. And I just fill in my equilibrium concentrations in terms of X, And what I can do here is I have a very, very, very small Ka value. So what that means is that my X is going to be super duper tiny. Now, granted, I'm subtracting it from something that is also very, very small. This X is going to be ridiculously tiny. So I can eliminate that, and also I can eliminate the 2.07 times 10 to the negative fourth because they're like quantities on the top and bottom, the numerator and denominator. So really what I end up with is 5.6 times 10 to the negative 11th as my X value. Now, ultimately, what I want is that hydronium concentration. So I will substitute that X value in for this hydronium concentration. You're going to see something really interesting happens here. So I want to take 2.07 times 10 to the negative fourth, and I'm going to add my X value there. So I'm going to add 5.6 times 10 to the negative 11th. Now what you're going to see is that this really doesn't do anything. I get 2.07000056, maybe I counted too many zeros there. This is outside, that little tiny change is completely outside of our quantity of significant digits here. So that second hydrogen coming off really did not do anything ultimately to the concentration of the hydronium. It changed it so little that we didn't even need to worry about it. So really, whenever you're solving a problem where you have a polyprotic acid, just worry about that first step, that first removal of the hydrogen. The second one or even the third one aren't going to be removed enough to really impact that hydronium concentration or change that pH very much. So ultimately, unless you're dealing with lots and lots and lots and lots of significant digits, if you're only out to 3 significant digits, you're probably not even going to feel the effect of that extra hydronium being created. Now here what we want to do is we want to find the pH of this substance. So the pH here is 3.68. And that's found by taking the negative log of the hydronium concentration. So when we have a polyprotic acid, just find the first dissociation, the hydronium ion created from the first dissociation. That's going to give you enough to give you a solid pH, and any hydronium that is created after that isn't going to be enough to ultimately change the pH value very much, if at all. So just calculate the pH based on that first step in a polyprotic acid.